Let me share my screen and we'll start to discuss. Is my screen visible?
Yes, sir.
Okay, so today we'll discuss about virtual memory management. So in the previous classes, we discussed process management, how a process is created, what are the various things that are associated with process, how CPU schedules various process, and we started discussing memory management, what are the various issues in memory management, how the memory is allocated in a continuous way uh, by using paging, uh, pages and frames, the relationship it will maintain in a page table that will help to allocate the memory in a continuous efficient way, which will avoid the external fragmentation and compaction. That all we studied in the previous class, and let us continue today's discussion on virtual memory management. So if you recall, there was one discussion happened in the beginning of the semester. uh, I asked a question saying that if your memory, say that you have only 2 GB, your in your laptop, if your memory is having only 2 GB, and suppose you want to play a movie which has memory say 4 GB, will your computer will be able to play that video? Can you answer? Can you think and answer?
No, sir.
So your memory is only 2 GB, but memory in the sense I'm talking about RAM, okay, main memory. But your hard disk might have more capacity. You can store the data in hard disk, but if your movie is say that 4 GB or 5 GB, more than your RAM size, ideally it should be more than your RAM size. Will your computer can play that movie in your system? So one person said no. What about others? Do you agree with him or you have any different answer? Say yes or no. Either say that it is not possible or say it is possible. No response. Okay. It's possible, guys. It's possible. Even though your data file, the video file which is having more than your RAM size, still uh, your computer can able to play that using virtual memory management. What happens is in virtual memory management, the data may stored in hard disk, uh, and some part of the movie only will brought into the main memory. It will execute, and after that movie is executing, whatever the things that are finished, it will swap and bring it the another part of that file. So the whole process or the whole program will not load at a time in the memory. Only part of that program is loaded for the time being. After that finished, it will swap that memory space for the upcoming uh, programs. So that happens because of this virtual memory management. So let us now try to understand what is virtual memory management, how we can able to do that. So virtual memory is a technique that allows that execution of process that is not completely in memory. One major advantage is that the programs can be larger than the physical memory. Even though your file is more than the RAM size, actual, when I say memory, it is RAM. I'm talking about RAM. So that is the main memory, right? So even though your file or the programs which are larger than your actual RAM size, still using virtual memory technique, you can execute that process by not bringing completely in the memory. So virtual memory abstracts the main memory into an extremely large uniform array of storage, separating logical memory as viewed by the programmer from the physical memory. So the programmer may see that this file is more and the RAM is size is less and it's not possible. You don't need to worry about that. Okay, this virtual memory technique frees the programmer from the concerns of the memory storage limitations. That's what this point is. Okay, this technique frees from the concerns of the memory storage limitations. Virtual memory allows a process to share files, libraries, and other implement shared memory, but it is not that easy to implement. Okay, it is not easy to implement. However, if we don't follow proper way of implementing the virtual memory, there will be substantial decrease in the performance. If you implement this virtual memory very carelessly, then your whole performance of the system will degrade. But we can do, even though our file is larger, then still we'll be able to play that. So because of this virtual memory, few benefits are: a programmer would a program would no longer be constrained by the amount of physical memory that is available. Users would be able to write a program for an extremely large virtual address spaces, simplifying the programming task. And because each program could take less memory, more programs could run at the same time, with a corresponding increase of CPU utilization and throughput, but no increase in the response time or turnaround time, because you are loading one few parts of the program, then more number of programs can be loaded. It will increase your CPU utilization and throughput. But because you are loading many programs at a time, and although you are executing those files, your response time and turnaround time will not increase. It will be decrease only. So less input output would be needed to load or swap portions of the program into the memory to each program that would run faster. So using virtual memory, we can able to do that. But if you have to see that how the virtual memory looks like, in the last time you see that the the number of pages were less than the physical memory. If you recall the previous class, the physical memory is bigger than the page size. Okay, something like this. So your page size may be like this. You have a page table, but your memory size is larger. Okay, ideally this will be the, now see here, the page is larger than the mapping, but the main memory looks smaller. The number of pages, uh, the number of physical memory is smaller than the virtual memory. So actually what happens is, when this is case, virtual memory can bring into the picture. Virtual memory can be larger size than the actual physical memory, but still using some memory mapping, uh, we can bring that data into the main memory for execution. And how we did swapping using backstore. If you recall the swapping we did in the last class in the memory management, we have a backing up store. We will keep swapping the files to bring it the main memory whenever it is needed until all the process got completed. Now we have to map in a such a way that the page faults, the memory mapping from the physical memory to the virtual address, this mapping should done in a proper way, so that even though this large file can able to replace the mapping, this mapping should be replaced frequently, so that this data will be loaded in the main memory frequently. That we have to look after how we can carry out this. But it is possible your virtual memory can be bigger size than your physical memory. So virtual memory involves the separation of logical memory pursued by the developers from physical memory. The separation allows extremely large virtual memory to be provided by the programmers when only smaller physical memory is available. So as a programmer, you may need extremely large virtual memory need to be provided, but only smaller physical memory is available. Then the virtual memory can come into the pictures. Okay, this is the same thing. Now, the virtual address space of a process refers to the logical view of how a process is stored in memory. So we have in the last class, if you recall, we have physical address space for physical memory, logical address space, logical memory. That logical address is generated by CPU. The physical address mapping to the logical address will be generated by memory management unit. Likewise, the virtual address space is also some process that refers to the logical or virtual view of how a process is stored in a memory. So usually when you look at this diagram, some virtual address is stored like text or data. We store stack and heap, where we can access the data. Okay, for example, when you're calling in C programming, you're calling functions. uh, Suppose, yeah, you say that, let me take the pointer. Okay, you say that, say factorial of a given number, you pass n. Okay, now you write inside something like this, right? Fact of, you're calling again, fact of n minus 1 multiplied by n, something like that, right? You write if n greater than equal to 0. Okay, you can write if n greater than or equal to 0 or greater than or equal to 1. You write this, right? Else, if n is equal to 1 or 0, you return 1. So you write this, return fact of n minus 1 into n, something like that. You write correct. This is called what? When a function calls itself, what is this called?
Recursion.
Right. What happens when you call recursion functions? How they are stored?
In stack.
Okay. So the program, the number of lines of the program might be less, but when this program expands, this every time when you call the fact function, that will store in the stack. Okay, that will store in the stack. You heard about dynamic memory allocation, malloc, calloc.
Yes, sir.
How they are stored? What is the data structure that is used inside the dynamic memory allocation? You use stack for recursion calling the functions, because that is the data structure you will use. What is the data structure
Heap.
that you use for dynamic?
Heap.
Heap. You will use heap. You explore that. If you don't know, explore that. Okay, so when a program or when a person, I mean, like when we are writing something, usually the memory is allocated and executed in virtual address space. So the stack is kept and it will move from top to bottom, maximum to bottom. Heap is kept at the below, it will grow from bottom to top. So this address space is empty. There is a large address space that is an empty space, which we call that as a hole. Okay, typically you can say that, you see, that's what I have written here. uh, the view of a process begins as a central logical unit, say address 0, in a continuous memory location. The large blank space or a hole, this is the hole between heap and stack, is a part of virtual address space that will require the actual pages only if the heap or stack grows. Okay, that will require the actual physical pages only if heap or stack grows. Now that virtual address space includes holes are known as sparse address space. Okay, the virtual address spaces that include the holes is called as sparse address space. Using this sparse address space, it's beneficial for the holes can be filled as a stack or heap segments, grow if you wish to dynamically link the libraries, or during the program execution this space can be used. But if using this address space, we will allocate the stack or a heap segments in the virtual address space. So this is something we need to understand. Virtual address space of a process in the memory, how it happens. But let us now try to understand how the virtual memory works actually. So consider an executable program that might be loaded from the secondary storage into the memory. So usually what will happen, from hard disk, you will move to RAM. From RAM, this is the main memory. This is hard disk, that is secondary storage. hard disk is secondary storage, this is primary storage. You'll move to RAM, then you'll move to processor, CPU, where you'll execute the instructions. But in between, there might be some other RAMs like cache to decrease the mismatch the speed. There might be cache, that is also fine. Registers, but ideally from hard disk to RAM, secondary memory to primary memory to CPU. One option to load the entire program in physical memory at the execution time is one way. So whatever the program you are executing, you completely load that entire program into the physical memory for executing. So the problem with this approach is we may not initially need the entire program in the memory. Loading the entire program in the memory results in loading the executable code for all options, regardless whether or not an option is ultimately selected by the user. Okay, whether you are after the program is executing, once you turn into exe file, whether the user is selecting some option or not, irrespective of that, you have to load the complete code into the memory. This is not efficient, okay, because the all the program is loaded in the memory, but only few parts that is user is selecting, that only will execute. Okay, that only will execute. Rest of the things, it will be in the RAM. If user asks, it will execute, otherwise it will not. That is the ideal way how uh, uh, typically the memory management will work. But there is an alternative strategy to load pages only when they are needed. So I will load, for example, when you are having this pages, you are dividing your program into number of pages, page 0, page 1, page 2, so on and so forth. Suppose your process say uh, takes only say that 3 pages. Your process takes 3 pages, and if you are loading into the physical memory, you have to load all 3 pages into the memory. Now all 3 pages may not execute, only page 1 is needed. Now I will, if the page 1 is only needed for executing, page 1 only will load into the memory, it will execute. A partial part of the code only will be loaded into the memory to execute. Then whenever there is a demand of page 2, page 0, they will execute. So demand paging says that the load pages only when they are needed. This technique is known as demand paging, which is commonly used in virtual memory systems. Okay, so instead of loading the entire program into the physical memory, we will load only the pages that are needed. Is this clear? What is demand paging?
Yes, sir.
Okay, so with demand paged virtual memory, pages are loaded only when they are demanded during the program execution. Pages are never accessed, or thus never loaded into the physical memory. Which are not accessed, which is not loaded. Okay, they will not load. Demand paging system is similar to paging system with swapping. So last time we understood that how the paging will work with page table and memory, but here there will be another part, swapping, where the process reside in the secondary memory, usually in hard disk or NVM device. Demand paging explains one of the primary benefits of virtual memory by loading the portions of the program that are needed, and memory is used very efficiently. I will show you something like that. Okay, so the demand paging will be used only the logical memory that are needed only stored. Now which data will be stored or which page should not be stored, how we will decide which page will be stored and which page is not stored. We will decide by one factor called valid and invalid bit, that we'll try to understand. Okay, so generally the concept behind the demand paging, as mentioned, is to load a page in memory only when it is needed. As a result, what happens when a process is executing, some pages will be in memory and some will be in the secondary storage. So the virtual memory address means uh, the entire program will be stored in hard disk only. Part of the program will be loaded into the memory, and rest of the program will be stored in the secondary storage only. So some pages will be in memory, some will be in the secondary storage, that is in hard disk. So we need to form a hardware support to distinguish between the two. So what happens is, every time when the program is completing its execution, that part of the program is, whenever it is needed, it will be loaded from secondary memory to primary memory by swapping. Okay, by swapping it will be used, it will be loaded. So to do that, we need a information hardware support called valid and invalid bit scheme, which is used for this virtual memory address. So when a bit is set to valid, then that page, whatever it is associated, is legal and in memory. If the bit is set invalid, then the page is not valid, that is not the logical address space of the process, or is valid but is currently in the secondary storage. So all the valid bits pages are stored in the memory. All the invalid bits, or which is not valid, are currently stored in the secondary storage. Okay. So for example, here in this case, let us say that 4, process 4 is E. Okay, sorry, my mistake. So 0, let us start with A. 0 is A, page 0 is A, that is stored in frame 4. So if this is a valid bit, in frame 4 A is stored. Okay, now page 1 is invalid, B is not needed to store. Now because this is invalid bit, B will not stored in the memory. Next, 2, page 2 is valid, so page 2 6, page 2 C is valid in frame 6, so this is stored here. D is invalid, D is not stored. E is invalid, it's not stored. F is valid bit, so this is stored in frame 9. Okay, likewise, but this all A, B, C, D, E, F, G, H, all are in memory, but only the valid bits are in physical memory. Remaining bits B, D, G, C, all this A, B, C, D, E, F, G, H, all these are in backing up store. They are in the secondary memory. Okay, you see that A, B, C, D, E, F, G, H, all of them are in a backing up store. Whenever it is needed, the swapping will take place. The swapping, last time we understood, like how page table works. Similar way, that process will be removed and the other process will be loaded. So in this way, what happens? You are using your physical memory very efficiently. Instead of loading all A to H into the memory location, you are loading only the parts that are needed, and remaining things you are storing in the secondary memory. And by making a valid or invalid, by demanding, I mean like by observing that these pages are in demand, that are only loaded, the not required pages will be not loaded. So this is called demand paging. Using demand paging, we can able to handle to some extent the virtual memory management. Is this clear?
Yes, sir.
Okay, so what happens when demand paging happens? When demand paging is introduced, what happens is, suppose ACF. Now I want DEF, DEG. Now what will happen? This memory spaces, for efficient use, what will happen is they will be replaced. They will be replacing either one of this process. If this memory space is available, then it may allocate or it may swap. It may swap the process. Okay. So what happens when a process tries to take a page that was not brought into the memory? Access to a page marked invalid causes a page fault. Means, I will tell you what that happens. Like, suppose now uh, you are having the process needs, the process is divided into, say, this many pages. Now you have a reference string. Now I say that A is required. Okay, A is in main memory, no problem. Now C, after C is required, C is also in main memory, no problem. F is required. Okay, that is also in main memory, no problem. Then I want to say that D is required. Now when D is required, assume that only 3 frames are available. Only 3 frames are available. Now when D is required, remaining are all occupied. Let us say that this is all space is occupied by other process. There is no free process. Assume that only 3 frames are available. Now when D is required, what will happen? D will be brought into the memory, replacing A. Now D will come, replacing only three memory spaces are required, right? So only now 3 is required. So whenever a process is swapping, replacing the another page, whenever a new page is replacing another page, which is called page fault. Page fault because that page is not there in the memory. This page D should be in the memory. Programmer assumes that all these pages are in the memory, but D is not there in the memory. So there is a page is not there in the memory. So this page is not there in the memory, and if it is observed the page table, D is written as invalid bit. 3 is not there at all. This 3, okay. 3 is page 3 here is invalid bit. Whenever there is an invalid bit, we call that as a page fault. Whenever page fault occurs, we will replace one process, bringing back to the memory, replace that swap with the next memory. When such thing happens, we call that as a page fault. Is this clear?
Yes, sir.
I repeat one more time. Whenever a page, when you're loading into the main memory, if that page is not available, how do you know it is not available? By observing the page table invalid bit. If the bit is invalid, then that page is not there in the memory. When there is an invalid bit, we say that the page fault occurred. Now what we will do is we'll make this valid by swapping this process with any one of this process. Which process should be replaced by D? Why A only should be replaced, C can be replaced, or F can be replaced? Yes, we have then again different strategies. Which page should be replaced by the new page? But whenever a new page is coming and it is not in the memory, then because of this invalid bit, we call that as a page fault. Okay, that's what we try to say here. Access to a page marked invalid causes a page fault. Now, the paging hardware in translating the address to the page table will notice that invalid bit is set, causing the trap of the operating system. So this trap is a result of the operating system failure to bring the desired page into the memory. Now, this is how typically happens step by step. Now, operating system is there. Now, we have the memory. We will load the memory will be looking into the page table. This page table is invalid. Then there is a trap. The trap will be observed by the operating system. Then it will go to the backing store. Page is on the backing store. Then bring that page to the frame. Free the frame. Any one frame you will free that. Reset the page table into make that is valid into invalid into valid. Then again load that page into the memory. Restart the instruction. The sixth stage. Okay, this is how happens. Steps handling in the page fault. The page fault, it is not in the memory. Whenever there is a page not in the memory will give a reference to the page table. Whenever there is a trap by the operating system, the operating system will go to the backing store. From the backing store, this is a secondary memory hard disk where the process is stored. It will bring into the frame and allocate by bringing into the frame, it will reset the page table. After page table reset, it will restart the instruction. Then again, it will be loaded. So whenever there is a page is not available, the page halt will be handled by the demand paging with these 6 steps. So the handling procedure in checking the statements what I explained is written here. We check the internal table for this process to determine whether reference is valid or invalid. If the reference is invalid, we terminate the process. If it is valid, but why we haven't bought into the page now? We page it in. If it is not there in the page, then we will page it in. We'll find a free frame, and we will schedule the secondary storage operation to decide page to the newly allocated frame. The secondary read is complete. We modify the internal table kept. See the fifth table, we'll modify reset the page table, which is kept in the memory, then restart the instruction, which is interrupted by the trap. The process now access the page as though it was in the memory. So these are the 6 steps it will happen. The details are given here. Now let us talk about page replacement. It is not that easy to replace a page. There are many things we need to study in this aspect. So page replacement takes the following approach. If no frame is free, then we have to find that is not currently being used and free it. If we can free a frame by writing its contents to swap space, changing the page table or all the other tables indicate that page is no longer in the memory. So we modify the page fault service routine, including the page replacement. Find the location of the desired page on the secondary storage. Find a free frame. If there is a free frame, use it. If there is no free frame, then use page replacement algorithm to select a victim frame. This page replacement algorithm, we will discuss, this is very important. Which if there is no frame, then some page should be replaced, some frame should be replaced. So we have to select victim frame. Which one will be replaced? That will be decided by the page replacement algorithm. We will discuss that, how the page replacement algorithm will work. So what happens when the page fault happens? We will find the desired page, whichever need to be loaded from the secondary storage. If there is a free frame, we will use it. If there is no free frame, we will select a victim frame. The victim frame is pushed to the secondary storage. Change the page and frame tables accordingly. Read the desired page into the newly fed frame. Change the page table and frame tables. Continue the process whenever a page fault is occurred. So something like this. So when a process PC will try to access the process B, logical process of 1, here it will observe, it is say that invalid bit, so B is not available in the memory. Okay, now what it will do, it will go to the secondary space, bring B into the physical memory, but B is need to be, the space is full. From here to here there is a kernel space, all this are full, so B has to be replaced by any one of this frame. That is called page replacement algorithm. We will discuss that. Okay, B will replace any one of this frame. Then after making that, after bringing and replacing this one of this, whichever it is selected, that will be stored in the secondary. Then that particular process will the process 2, it will make the valid and invalid bit. Okay, now it will be valid, then it will restart. Okay, it will restart. Okay, something like that. So need for page replacement. Okay, now something like this. So you have a frame, valid or invalid bit. So whenever there is a victim page out, we will select that this is the victim. We will change that bit to invalid to valid. Then the desired page will be stored in that frame. Reset the page table. Okay, step by step. Step 1, page out this. If you select this frame, this will be stored back into the secondary memory first. Whatever the victim that you are selecting, step 1, you will store that page into the secondary memory. Step 2, whatever the page you want to load, you will change that bit to valid to invalid. Step 3, you bring that page into the frame. Then step 4, whenever you are bringing a page to the particular frame, update the page table. Make it a valid and the frame number. Okay, so this is how the page replacement works. Now there are many page replacement algorithms. We will try to study. Maybe we will not get to finish all the time, but at least one we will study. One we will study. Rest of the things we will study on Thursday's class. So let us now try to understand how the page replacement algorithms works before. So the simplest page replacement algorithm is first in first out algorithm. So first in first out replacement algorithm associates with each page the time when the page was brought into the memory. When a page must be replaced, the oldest page is chosen. We can create FIFO queue to hold all the pages in the memory. When we replace the page, the head of the queue, when a page is brought in the memory, we insert the tail of the queue. For example, let us say that these are the pages you want to bring. This is a reference string. So this is page 7, page 0, page 1, page 2, something like that. Okay. There are different pages that want to bring, and you have only 3 frames. These are the page frames. Okay. So initially these 3 frames are free. So 7 is stored here, no page fault. 0 is stored, no page fault. 1 is stored, no page fault. Now the 2 is coming. When 2 need to be kept in the frame, there is no free frame available. Then first in, first out, whichever comes first. 7 came first, so this will be replaced. 7 will be replaced by 2. Okay. So here 1 page fault occurred. Sorry, you can consider all this. Initially, whenever you are inserting a new item, you can keep that. Okay. So now see that 7 is replaced by 2. Here some changes happen. Now next bit is 0. 0 is already there, so there is no need of replacing. A new bit is coming. See, 2 is coming here. There is no place, so 2 will be inserted by replacing the 7, because this is FIFO. Whichever comes first, that will go out first. So 7 will be replaced by 2. 0 will come next. 0 is there already, no need. 3 will come. So 3 will be replaced by the second bit. Okay. 0 will be replaced by 3. Next 0 will come. 0 is not there in the frame, so it will be replaced. 1 will be replaced by 0. Next 4 will come. 4 is not there here, so the last replaced was 2. So 4 will be replaced. 2 will be replaced by 4. Next 2 will come. 2 is not there here, so 2 will be replaced. 3 will be replaced by 2. Next 3 will come. 3 is not there in this frame, so again 3 will be replaced. Then 0 will come. 0 is not there, again 0 will be placed. Next 3 will come. 3 is already there, no need of page fault. 2 will come. 2 is already there, no need of page fault. 1 will come. 1 is not there, so what is the recently replaced bit? 0, right? So after that 2 will be replaced. 2 will be replaced by 1. Next bit replaced by 3. 3 will be replaced by 2. So next is 0. 0 is there, it will no page fault. 1 will come. 1, there is no page fault. 7 will come. Next the bit need to be replaced by is 0. So 7 will be replaced. Next 0 will come. 1 will be replaced. Next 1 will come. It will be replaced by 2. So FIFO page replacement happens. This is the head of the queue. This is the front of the queue. This is the tail. Okay. Now whenever initially both will be at the beginning, tail will be at the beginning, front and tail. Front and tail will be pointing at the same end. So front is there. Now next element, front will move. Front will be there. Front will be here only. You delete at front, insert at rear. Okay, insert at rear, front and rear. So insert here, rear will be inserted, RF. Then again R will move here. Now 2 will come. 2 is not there, so we need to delete, right? We need to replace. Which one need to be deleted? Front will be deleted. So this will be deleted. So 2 will be replaced. So front will move here. Okay, this element is deleted. Front will move here. Now 0 will come. 0 is there already. 3 will come. So front will be deleted. So front will go to third position. That will be replaced. 3 will be replaced by 0. Next 0 will come. So front again. This will be deleted. 1 will be deleted. 0 will be inserted. Next, friend will point to beginning, right? Friend will point to, after replacing, 0 is replaced, then friend will point here. So 4 will come, 4 is not there here, so friend 2 is replaced. Next, friend will point here. Next 2 will come, 2 will be replaced by 3. Friend will point here and 3 will be replaced by 2. Next 3 will come, friend will be replaced again. This element is deleted. Friend will become here, 0 will be replaced by 3. Then 0 will come, friend will be replaced. Friend will go to next element, 4 will be replaced by 0. 3 will come, 3 is already there in the queue. 2 will come, is already there in the queue. 1 will come, 1 will be replaced by 2. Friend will go to here, 2 will be replaced by 1. Next 2 will come, 2 is not there in the queue, so this will be replaced, 3 will be replaced. Friend will go to top, first element, then 2 will be replaced here. 0 will come, 0 is already there. 1 will come, is already there. 7 will come, so friend will be moved to here. Next element, 7 will be replaced. Now 0 will come, friend will be moved to the next element. 0 will be kept here. Then 1 will come, 1 will be replaced by the element. Next element will be replaced. The new element is coming is friend will move to here. So 2 will be replaced by 1. So this is first in, first out page replacement. Is this clear how this page falls occurs?
Yes, sir.
So how many faults happened? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, total 15 faults. Okay, so whenever the replacement will happen from the secondary memory to the main memory, every time when the page is there already, then there is no fault. When there is a new page is coming which is not in the memory, then you have to replace it using page replacement algorithm. So in this case 15 faults happen. So when you follow FIFO, that's what happens. So this is a very simplest page replacement algorithm, first in first out. So which associates each page with the time when the page was brought into the memory. The page is replaced, the oldest page is chosen. We can create a FIFO queue that will hold the pages in the memory. So we'll replace the head of the queue, that is the front of the queue. Whenever a page is brought in the memory, we'll insert it at the tail of the queue. So that's what we did here. So with this example, we observe that FIFO will have 15 page faults. First 3 references, that's what I explained. 701 cause page faults because they are brought into this empty frames. The second reference 2 replaces page 7 because 7 was brought into the first. Since 0 is the next reference, I explain the same thing. What I explained here, I have given here. So each process will be done by this. So every time a fault occurs, we show that pages in our 3 frames. So there are 15 faults altogether. FIFO replacement algorithm is easy to understand program, but however the performance is not always good. One hand, the page replaced by the initialization model that was used long time ago, which is no longer needed, that is good. On the other hand, it could contain a heavily used variable that was initialized early and in constant use. When that happens frequently, replacements will happen. So FIFO replacement algorithm is easy to understand and program. However, the performance is always not good. That's what we studied. Okay. So a bad replacement choices increases the page fault rate and slows the process execution. If it does not, however, cause the incorrect execution. So what happens? You see that to illustrate how bad it can happen, the bad replacement choice. So consider this following reference string 1, 3, 4, 1, 2, 4, 5. Okay. Now let us try to apply with, let us say that you have one page fault. So only one frame, the number of frames, the x-axis is number of frames. You have only one frame. So how many page faults is required? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? There are only one frame. Only one frame is available. Every time you bring you need to replace. So 1 will be there first, next 2 will come, 2 will be replaced by 1, next 3 will come, 3 will be replaced by 2, next 4 will come, 4 will be replaced by 3. So the number is not any number is the same after the next element, so it will cause the number of pages only. So this will cause 12 page faults. You have 12 numbers. Is that correct? This value is correct. If you keep the number of frame 1, the number of page faults is 12. You keep two frames, what will happen? Next, first 1 is stored here, next 2 is stored. Next, what will happen? 3 will come, 1 is replaced by 3. We'll do it again. Okay, let us take 2 page faults. Okay. So initially 1 will be stored. Next 1, 2 will be stored. Next there is no frame, only 2 frames are there. Number of frames is 2. Next 3 will come. So 3 will be replaced 1. Next 4 will come. 3, then 2, 4 will be 2 will be replacing 4. Next 1 will come. So 1, 4. Next 2 will come. 1, 2. Next after 1, 2, 5 will come. So 5, 2. Next 1 will come. So that frame is not there. So again 5, 1. Next 2 will come. 2, 1. Next 3 will come. 2, 3. Next 4 will come. 2 will be replaced. 4, 3. Next 5 will come. 4, 5. How many page faults happened? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for 2 frames also the number of page fault is 12. Let us consider 3 frames. What happens? Can you tell me how many page faults when 3 happens? So 1, 1, 2, 1, 2, 3. Next 4 will come. 4 will be replaced by 1, 4, 2, 3. Next 1 will come. 4, 1, 3. Next 2 will come. 4, 1, 2. Next 5 will come. 5 will be replacing this one, right? 4, 5, 1, 2. So next 1 will come. 1 is already there. 2 will come. 2 is already there. Next 3 will come. 3 will be replacing 5, replacing 1. 3 will come. Next 2. Next after 3, 4 will come. 4 will replace 2, 5, 3, 4. Next 5 will come. It is already there. So how many page faults here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So for 3 number of frames, the number of page faults is 9. Okay. So you increase the number of frames, 4 frames, then What happens when you increase 4 frames? Let us see that. Now we will take 4. Okay, first 1, 2, 3, 4, it will take 4 page faults. Okay, 1, 2, 3, 4, it will take 4 page faults. Up to this point, 4 page faults. Okay, next bit, 1 will come, it is already there. 2 will come, it is already there. 5 will come, so 5 will be replacing 1. 5, 2, 3, 4. Okay, up to this we finished. Next 1 will come, 1 will replace 5, 1, 3, 4. Next 2 will come, 2 will replace 3, 5, 1, 2, 4. Next 3 will come, 3 will replace 4, 5, 1, 2, 3. Next 4 will come, 4 will replace 5, 4, 1, 2, 3. Next 5 will come, 5 will replace 1. Right? Sorry, 4, 5, 2, 3. How many page faults? 4, 5, 6, 7, 8, 9, 10. Total 10 page faults. If the number of frames is 4, then you are increasing 10 page faults. For some page replacement algorithms, you can observe that the page fault rate may increase as the number of allocated frames increases. Ideally, if the number of frames increases, then the page fault should decrease, correct? When the number of frames are increasing, the page fault should decrease. But for some cases, when the number of frames are increasing, the page fault is increasing. This is called Belladay's anomaly. Okay, this is called Belladay's anomaly. When the number of frames are increasing, page fault should decrease, ideally. But here, the number of frames are increasing, but still the number of page faults are increasing. It's not decreasing. So this is called Belladay's anomaly. Is this clear?
Yes, sir.
So that is the main problem of FIFO replacement algorithm. So bad replacement choice may increase the number of page fault rate and slows the process execution. If does not, however, causes incorrect execution. If it is not causing so slow process, then it may cause the incorrect execution. So we need to be very careful when we are using. That's why FIFO page replacement algorithm is not always good. Okay, so it's not always good. So this is the main drawback of FIFO replacement algorithm, and the number of page faults in this case is 15. And we will try to observe by evaluating with other page replacement algorithms. We'll try to see whether we'll be able to decrease the number of page faults or not. So that we will discuss in the Thursday's class. So we'll stop here up to this point. If you have any doubts, you can ask. So this is repeated slide. This slide is already there. So okay. So up to this point, we will discuss. If you have any doubts up to this class, up to this slide, you let me know. Otherwise, we will discuss the rest of the things. We'll discuss in Thursday's class. Basically, the idea is instead of storing all the file, we will store only part of the file and execute. The rest of the files will be in the secondary storage. When we do that, we call that as a virtual memory management. So ideally the files are there, but it is not completely loaded. Okay. If you don't have any doubts, we will stop here. We'll continue on Thursday's class. You can leave. Okay, so nobody is asking any doubts. So we'll meet on Thursday's class. We'll continue our discussion on page replacement algorithm.